area of island. You are given an m times n binary matrix grid. An island is a group of ones representing land connected for directionally or horizontally or vertically. You may assume all four edges of the grid are surrounded by water. The area of an island is the number of cells with a value 1 in the island. Return the maximum area of an island in grid. If there is no island, return 0. Example 1, we have our visualized grid, matrix grid, and um, breaking down over here. So we can see here are we have the output 6, so that means the maximum we have island is this. So these two are not connected because it has to be horizontally or vertically. Since there's none that connects them, um, it's 6, not 11 as it shows over here. So this one is simple, everything is 0, so we're going to have 0. We have no islands in it. So now let's get into this. So we can solve this. We will solve this via number 1, depth first. I'll start with BFS first. So let's say the best for last. 1 vert first search. It's the best because it's shorter to do, not anything else. Depth number 2, depth first search. So now let's make our number 1 BFS function. DFS BFS, def BFS. Let's put R, start with R and C. That's row and column. And so with BFS we can just go ahead and just make our Q and make DQ and then put RC in it. Let's call grid RC. Let's mark it to 0. Equals to 0. Mark carried so to 0. So now let's go ahead and initialize area to 0. Initialize area to 0 to start off with. So now let's get into this while loop. So while we still have a Q, while Q, let's count the next island. So while Q, let's pop it off. Let's call RC NR, and then NC equals to Q dot pop left, and then once we pop it off, let's add area equals to 1. Count our next island, our next one. Next cell in our island. So now we have that. So now let's make our directions to move. So let's go directions equals to let's make our list individually and our v plus 1, which is going down, nc, and then move up, and minus 1 nc, and then move left. So that will be nr nc minus 1, and then move right. The last one, nr nc plus 1, and that seems to be all of it for now. So for nx, and this will be our new direction, and nx directions, nx and y and directions. Let's take let's call it let's check if it's within bounds. Check if in bounds. Wait. If in bounds, then take q. If 0 is less than or equals to nx, which is less than the length of grid, and then let's make and 0 is less than or equals to ny, less than the length of the grid 0, and it also, so this is to make sure that it's within bounds. So grid 0, nx and y is equals to 1. So once we meet all of these, then we can go ahead and add it. So q, let's add it to a q, to append nx and y to our next, for it to be part of next. So now let's make our grid nx and y to be equals to 0. Mark it to 0, and that seems to be all of it for our BFS function so far. So return area. So let's see if there's anything that needs to be fixed immediately. That seems to be it. So now let's initialize our max area equals to 0, starting from 0. Initialize our max area. So for I, or we call R, and the range of the length of grid, for C, and the range of the length of grid, if grid C equals to max max area dot BFS RC, and let's move out return max area update. But this is simple to be able to tell. So whichever is larger, our current max area, or the one that we get from here. So that's what it's going to update as our max area. So let's see if there's any syntax errors. And there doesn't seem to be any. Let's see if it works. If line occur and y is oops, it should be inside. I think that's it. Let's see. And it's been accepted. So that's it for our BFS function. It can take some time to learn, but it's not difficult. So now we save the best for last. By best, it meaning that it's shorter to do. It won't be as long to do as the BFS, because DFS calls it recursively. So now let's make our recursive function. Number 2, DFS function. So now DFS dot row and column. We can just make it this, but let's just call it this to differentiate it somehow. So if not within bounds or cell is 0, return 0. So that will be so if row is less than 0, or row is greater than or equals to the line of grid, or call is less than 0, or call is greater than or equals to the line of call is greater than yes, green 0, or grade call and row. Oops, row should come first. Row call is equals to 0, return 0. So now let's mark our cell. So same concept over here. Mark current cell to 0. So once we call the BFS function, this is what's going to happen once we're able to get past this. So grade row call equals to 0. So we'll make area equals to 1. So starting set area for each island. So now let's make our directions So that'll be actions will add to our area. So area will be equal plus or equals to it's called the DFS function recursively call it. So that will be row going down, call area plus equals to DFS row minus 1, call area plus equals to DFS row call area plus equals to DFS. Oops, forgot minus 1 or plus 1, whichever. I'll put minus 1. So the call. So now if we have to do plus 1, and that's basically it. This one is much shorter than this. So let's see. It has the same, about the same concepts as this, but much shorter code. So now we have check to make sure that it's out of bounds. If all of them are out of bounds, we get return 0. Return area. So now let's make our max. Return will be equals to 0. So now let's traverse and update traverse grid and update max area. Why do I have max return over here? Max area. So for call in the range of the length of a grid, for row in row and call in the range of length of grade 0 if call no if grade call why am I writing call first before row? Row call and is equals to 1. So the same exact concept as this. So max area will be equals to max of whichever is larger. So area and then DFS row and call. So now let's see, return max and then return max area. So let's see if there's anything that needs to be fixed here. If not, if this greater than this, and that seems to be it. Let's see if it works. And it's been accepted without any syntax errors. So these are it. So this one is much shorter than this. That's why we saved the best for last. So our time and space complexities. Our time complexities and wait, let's do our time complexity first. Time complexity is equals to O of M, a row of M times, and our space complexity is equals to O of also O of m times n. So this is for row and for row and column for Q and so Q and space complexity is yes, Q and grade. So that seems to be it. Let's submit to see if it's going to pass all cases. And it's been able to pass all cases quite efficiently, but this isn't too accurate all the time because I do submit the same solutions. Sometimes it comes much less than this. And that's it for this problem.